Okay, so we have a test coming up on sections 4.1 and 4.2 that deals with extrema and Rolle's theorem and mean value theorem. So let's do a few practice problems to get us ready for the test. All right, the first one, of course, always read the directions. Find any critical numbers of the function. Well, the critical numbers are just the x values of our extrema, the x values of our peaks and valleys. So of course we want to take our derivative and set it equal to 0. F prime of x is equal to 3x squared minus 6x. And we're going to set our derivative equal to 0. And it looks like I can factor out a 3x, leaving x minus 2 in the parentheses, and that's equal to 0. So we have two factors multiplied together equal to 0. Use the zero product property that says we can set the first one equal to 0 and get x equals 0. And we can set the other factor x minus 2 equal to 0 and get x equals 2. So there we found our two critical numbers of this function. Again, we set our derivative equal to 0. Okay, now here it says locate the absolute extrema of the function on this closed interval, and we're going to do it algebraically. Okay, the extrema are ordered pairs, x and y coordinates. One of them will be our min, and the other will be our max. And I guess that is the absolute min, ab min, and ab max. Absolute min and absolute max. So first, we look for the critical numbers. Are there numbers inside the interval from -2 to 1 where we would have possible mins and maxes? So we're going to take our derivative and set it equal to 0. H prime of x is -2x plus 3. And we're going to set that equal to 0. And we add, subtract 3 from each side. -2x equals -3. Divide by -2, and you get 3 halves. So we have a critical number of 3 halves. Well, how can we have both a min and a max if we only have one critical number? Well, don't forget to check your endpoints. So what we're going to do is find, let me give myself a little more room here to work. Here's where we go back to the original function, h of x. We're going to do h of the left endpoint, -2, and see what comes out. And then we're going to do h of 3 halves, our critical number we found on the inside. And then we're going to do h of +1 and see what comes out. You can crunch these out on your calculator, or they're not too bad to evaluate in the function. But when you plug a -2 back into the original equation, out pops a -15. So that's the ordered pair, -2, -15. If you plug in the 3 halves, out pops a -2.75. So we could have that as 1.5, -2.75. And the last but not least, h of 1. If we plug a 1 in there, we're going to get a -1 plus 3, which take us to +2. Minus 5 would take us to -3. So that point is 1, -3. All right, which of those is our absolute min? What is the lowest of all of them? That'd be this one right here. -2, -15 is our absolute min. And what's the highest of all our y values? Well, this one, it's negative, but it's the least negative of all of them. So that'd be the point 3 halves, -2.75. So those are the absolute extrema. This here also is an extrema, a min or a max. A local min or max. It's a peak or a valley by itself, but it's not the highest peak or the lowest valley. We found our absolute min and max right here. This one is all on the TID9, so you're going to have to bear with me. I'm not going to bring up any kind of display screen, but it does say find all the extrema of this function on the closed interval. Well, here's our function, and probably the easiest way to do this would be to graph it in the y editor. And if you do that, you're going to get something that looks a little like this. It is even, positive even, so its end behavior is up on both sides. But we do have a -x cubed and a +x and a +1. That puts some kinks through the middle of it here. And let's see what happens. Here's where we would want to be. We're going to be on the graph screen. And you'll use the F5 drop-down menu. And one of those options is min. So So you do F5, drop down menu, choose min. It will ask for the lower bound. Well, get your little flashing cursor. Ooh, I should do this. Get your little flashing cursor somewhere here, on the left-hand side of this valley. And you'll hit enter for a lower bound, and then it'll ask for the upper bound. Use your cursor to bring you over on this side, and hit enter again, and it will give you, at the bottom of the display, the coordinates of that min, and that's negative 0.366, comma, and then 0.75 is your y value. Okay, again, F5 menu, use min again, and get over here on the left of this valley for lower bound, hit enter, and then move it over here with the cursor, hit enter again for the upper bound, and that will give you another min, and that one is 1.366, rounded, and also has a y coordinate of 0.75. Okay. F5 menu again, choose max. You choose max, it'll ask for the lower bound, get to the left of the hill, hit enter, it'll ask for upper, so you go over the hump to the other side, hit enter again, and then it spits out the coordinates on the bottom of the display screen, 0.5, comma, 1.31. Okay, they're asking for all the extrema, not just the absolute mins and maxes. Well, we know for sure, this is a min, and the other one was also a min. We could tell by the graph, of course, that it's the bottom of a valley. And this is going to be a max. So are those all our mins and maxes? Would those be the absolute extrema if they were asking for that? No, we got to check also our endpoints. Back to the original function. If you do f of negative 1, out pops a 3. And if you do f of 3, the right endpoint, you get 31. So there are some other, here would be our absolute max. That's the highest of all of them, and it does occur at an endpoint. And then we have a couple mins. These would be also our absolute mins, and they tie. We can have a race can have a tie if two people finish at the same time. These mins are also our global mins. They're the lowest our function achieves across the interval from -1 to 3. Okay, let's see what's happened here. Number 4. Okay, a couple days ago we did sort of like a warm-up or an in-class problem. Very, very similar to this. It might have been x times the radical, and then there was something different under the radical, but it's the same idea. You got two terms multiplied together. One's just an x, one's got a radical. Step 1, find the two x-intercepts of the function. Well, we find x-intercepts by setting our original function equal to 0. And this is nice because it's already factored. We have this factor times this factor. So we set our first factor equal to 0 and get x is 0. And we set this one equal to 0, while a -1 would 0 out under the radical. So there are our two x-intercepts. Again, if we want to think about this graphically, here's x, y. 0 is an x-intercept, as is -1. So we know we're crossing the x-axis at those points. And for the second part of the problem, then show that the derivative is equal to 0 at some point in between the intercepts. Okay, well, we're going to have to derive this. We have two distinct functions. First one, its derivative is -3. Here we have x plus 1 to the half power. Its derivative will be 1/2 quantity x plus 1 to the negative half power. That's supposed to be a 2. Okay, let's product rule this. F prime of x, our derivative of the f function is first times the derivative of the second, -3/2 x times the quantity to the -1/2 power, plus the second times the derivative of the first. So that's going to be -3, so this will turn into a -3 times x plus 1/2. Now, we've used this quite a few times in class, and I just like to beat you over the head with it. We have a very great simplification tactic called factoring out the least powers, because we do want to set this equal to 0. I mean, how could we set that equal to 0 right now? We want two things multiplied, not added or subtracted, so we could set each of those factors equal to 0. So let's factor out the least of the powers. So I see the same quantity, x plus 1, to different powers. Well, I want to focus in on the lesser of the two. Of course, the negative one will be the lesser, so that's getting factored out. So let's see, here's our first term. We have factored this out in its entirety, so we're left with minus 3 halves x minus, okay, here the 3 is going to stay, and then we're going to have the same quantity, but to a different exponent. So what exponent goes up here? Well, remember, when we multiply like bases, we add exponents. So this exponent, negative a half, plus this one should add up to positive a half. Well, of course, that's got to be positive 1, and that's what makes this such a great simplification technique. Is now that we have that quantity to the first power, the parentheses are meaningless, so we can ignore the parentheses. This, I am going to put it back into radical form, x plus 1 under a radical in the denominator, and that's going to be multiplied by this. We're going to distribute the minus 3x, so we have minus 3 halves x minus another 3 halves x, which is 6 halves x. So if we combine those, we get minus 9 halves x, and we distribute the minus 3 in here, and it'll be minus 3. So now we have two factors multiplied together and set equal to 0. Get rid of a little bit of this again. There we go. So where would this function become equal to 0 or undefined? Let's see the first term here. Where would this equal 0 or be undefined? It's where our denominator would equal 0. And that would only happen if x is equal to negative 1. Negative 1 plus 1 would 0 that out, and we have a divide by 0. So that's where we are not differentiable. This other factor, negative 9 halves x minus 3 equals 0. Well, I'd run a 2 through that, multiply through by 2, you get minus 9x minus 6 equals 0. Add 6 and then divide by negative 9. X equals 6 ninths negative, which reduces to negative 2/3. So is that it? Are we done? Have we answered the question? Well, let's see. Find the two x-intercepts of the function. Yes, we found those. I did erase a little bit of that. It was between 0 and negative 1. Then show that the derivative is equal to 0 at some point in between. Well, we took our derivative, we set it equal to 0, and we got this number. Is negative 2/3 between 0 and negative 1? Yes, it is. Somewhere in between there, we do have an extrema with a horizontal tangent line. Okay, these directions apply to the rest, numbers 5, 6, and 7. Determine whether Rolle's or the mean value theorem can be applied. Find all values of C guaranteed by that theorem. All right, well, first we've got to figure out which theorem we're using. So we check our endpoints. F of 0 and f of 3. So if we plug 0 into this function, of course, out pops a 0. If we plug in a 3, we get a negative. 3 squared is a negative 9, plus 3 times 3 is positive 9. Negative 9 plus 9 is 0. So our endpoints are at the same height, and that tells us we're going to be using Rolle's theorem. If we use Rolle's, we set the derivative, f prime of x, equal to 0. So let's take our derivative. F prime of x will be minus 2x plus 3. Let's set that equal to 0. Subtract 3 from each side. Divide by negative 2. X is 3 halves. So that was the value of C guaranteed in the interval. You know, here's our C value. X is 3 halves. If we were to graph this function, at that x value, we would have a horizontal tangent line. You know, if we wanted to find the exact location of it, we could plug this x back into the original function and find the y value that's paired up with that x value. But they were only asking us for the value in the open interval guaranteed by the theorem. There it is. Number 6, same directions. So let's check our endpoints. We got to figure out what theorem we're dealing with. So f of 0 is the sine of 0, and the sine of 0 is 0. And 2 pi. The sine of 2 pi is also equal to 0. Endpoints, same height, tells us we're going to be using Rolle's theorem. So for rolls, we set our derivative, f prime of x, the derivative of sine is cosine, set cosine of x equal to 0. All right, think about unit circle. Cosine values are x values. Where on the unit circle are x values equal to 0? Well, that's right on the y-axis. So top and bottom of the unit circle. What are those radian angles? Top of the unit circle is pi over 2. Bottom of the unit circle is 3 pi over 2. And that's all they're looking for there. All right, last one. Yeah, it is the last one, number 7. X cubed. Well, let's check our endpoints. F of 0 is 0. F of 1 is 1 cubed, which is 1. We have different height endpoints, so this is going to be mean value, MVT. So we got to find the slope between those points. The m, the slope of our secant line, is 1 minus 0 over 1 minus 0, which is 1 over 1 or 1. Our slope is 1. So we're going to take our derivative and set our derivative equal to that slope. Easy enough. F prime of x is just 3x squared. If I set that equal to 1, I divide both sides by 3, and I take the square root. X will equal plus or minus the square root of a third. Are both of those answers good? Well, remember here, we're only looking from 0 to 1. So the negative root of a third will not work. We're just going to focus in on the positive square root of a third. Let's do our numerators and denominators separately. Well, the square root of 1 is 1. The square root of 3 is the square root of 3. Can't be simplified. And let's rationalize. Multiply top and bottom by radical 3, and you get the square root of 3 over 3. So again, that is the x value or c value guaranteed in the interval by the mean value theorem. Now these can be a little confusing. Let's think about this as a quick graph. Okay, we're stuck in the first quadrant from 0 to 1. Our function is cubed. 0 cubed is 0. 1 cubed is 1. And that graph is going to look a little like this. Nope, not quite that extreme, but close enough. Okay, and what we did first is we found our endpoints, 0, 0, and 1, 1, and we found the slope between those points. So I can do this. Oh, I didn't want to do that in black. I wanted it in red. So here's the secant line. Now what we want to do is find a point of tangency, or the tangent line will be parallel to this line. And we found that as square root of 3 over 3. That's approximately 0.577. 0.577. So a little bit past the halfway point, here's our guaranteed c value, that if we were to go up to the function and there'd be a tangent line there, that tangent line is going to be, whoa, that's pretty terrible. Ooh, why don't I do this? I can copy that and paste it, and I'll just move it over, and it's got to be parallel. So there we found the x value, or here we're calling it c, that will give us a tangent line that is parallel to this secant line. So again, to sum it up, for rolls, you set your derivative f prime equal to 0. For MVT, you set your derivative f prime equal to the slope of the secant line through the endpoints. That's supposed to be secant m of secant line. And there we go. Good luck on the test.